In practice, whatever we use is based on this mini batch stochastic gradient descent, but we need to just do a bit of twist on that, which we talk about in chapter 3 as hopefully today. But one thing is that like you do this and you train your neural network, right? So for instance, we had that particular neural network we use for classification. You just train this neural network, right? So you have 60,000 MNIST images. You just go over it for 10 epochs. Now you would say, well, this guy is trained, right? Now, how you can test this trained network? You need to do inference on that, right? Meaning that you get a new sample, right? So you're going to get one new sample x new. This is one image. It looks like MNIST image. It is not one of them that you use for training. Because obviously, if you take one of them that you use for training, that one should work fine, right? Because your neural network already got trained on that. It tried to make the output exactly the same as what is inside the data set, right? So you don't want to use it because that's obvious that the neural network can do it perfectly, right? You want to get a new data, which is looking like MNIST. So this is, again, one MNIST image, but it was not given to your data set before, right? So this is one x new, and you need to know what is the true label, right? So you need to know this is 2, right? Because, of course, at the end of the day, you want the neural network to tell you, but now you want to test it, right? Now, you know that this is image, and this is image of digit 2. Then you give it to your neural network. You look at the output of the neural network. You see whether this is really 2 or not, right? Whether it's classifying as 2 or not. If it's classifying as 2, you would say, OK, that's fine. If not, then there is a problem with my training, right? My neural network could fit very well into my data, but it's still not what we call it generalizing, right? It's not able to just do it on a new data as well. So this is what we do in practice. So in practice, we are going to get X, a new sample, and then we pass it through our neural network. Typically, what we compute when we want to test, we do not only check the accuracy of the neural network. It means that I do not get one image and say whether this is really 2 or not, right? Because if it is classified as 2, I mean, you do know that the output of your neural network is computing a probability, right? Now, if you have a binary problem, if the probability of the true label is 0.55, you're going to get accuracy, like a correct classification. If it is 0.9, again, you're going to get correct classification, right? But you prefer your neural network to do 0.9, not 0.55, right? Because in the case of 0.55, this means, yeah, your neural network is not very clear, right? Just maybe it was out of the chance that it happened to get classified correctly, right? So we typically compute the loss as well. So this is, for example, the cross entropy. We're going to look at the output of the neural network. We'll look at the sample that we have, the label of the sample that we have, and we have not shown it to the neural network before, and we see what is the loss, right? This is what we call the test loss. Another thing is the test accuracy, of course, same thing that I said initially. So you compute your output, you see what's going to be the classification. You're going to say it's digit 2, and then you are going to compare it to the true label of your data, right? OK, if the true label is 2 and the output is 2, then you would say accuracy is 1. If the true label is something else and it's classified as 2, then you're going to say accuracy is 0. It's not classifying, right? Correctly. Everybody's clear, right? So this is for one sample. But say that I tried one new sample and this worked fine. Can I trust that neural network? No, maybe that was a chance, right? Again, I need to just average it over enough number of samples, right? So what we do in practice, we do not do it for one single point because this is not reliable. It is very high variant, right? It's going to have high variance, right? So what we are going to do, we are going to just go over what we call a test data set. So I told you, you have 70,000 images inside MNIST. You put 10,000 aside. Typically, 10%, 20% is something like classic, that you put 10 to 20% of your data aside. You do not touch it because you don't want your neural network to know about that. You just give the rest of it, right? The 60,000. It's going to get trained on that one. And then you just go over a test loop. What is a test loop? I go over all those samples inside this test data set. I do the same thing. I pass it. I compute the loss. I compute the accuracy, right? Now, say, for example, you have 10 different test samples, right? And then you try your neural network to classify them. Nine of them get classified right. One of them gets classified wrong. What is the average accuracy you see here? It's 90%, right? So your neural network in 90% of the tests you have done was successful. In 10% of them was not successful, right? So this is what you do. You're going to go over your test data set, and then you're going to compute test loss, test accuracy, and then you average them over the samples that you have used for testing. This is going to give you the test result for that particular neural network. Now, so that average is going to just approximate the test risk. This is what we usually call it the generalization of your neural network, because it's now running on data that it has not seen. If it's working fine, your neural network is generalizing. So it's really understanding the pattern, right? It's really understanding that 2 looks like this, right? Whereas if it does not work, if you get very low test accuracy, it means that your neural network has not yet understood the pattern, right? It just memorized things, right? Like it said, that image is 2, that image is 1. It didn't look into the image, right? Because if it looks into the image, for the new image, it should be able to do it, right? So you're going to compute these 2 things, the risk and accuracy, and this is going to be what you're going to get, out of your testing, right? So you train, you test it on the data set. This is what you get as the test result. If the test result is good, you're fine. If your test result is not good, you should again get back to your training and see what was wrong there, right? Questions? Yeah. You mentioned that when you test that, it would be 10 to 20%. You're right.
But is there a way to know what is the sufficient number?
No, you cannot say it. You typically.
I mean, for the training set.
For training set, again, no. I mean, the more the better, definitely, okay. Right? Yeah, but you cannot say. I mean, it depends on the samples you have. I mean, MNIST is obviously good. It has 70,000 images, but sometimes in practice you have 500 images, 500 samples. What you can do? Yeah, 50 aside, 450 I use, or maybe 400 I use for training, 100 for testing, right? You can not do anything more than that.
There's no minimum.
There's no minimum, of course. You can always increase, right? The more you have, the better you would be, right? But in practice, you are limited, right? But this 10 to 20% is just a rule of thumb to just get the idea. You want more data for training than testing, because you need your neural network to see lots of samples to get the pattern inside them, right? So questions? Everybody's cool, right? Now, one thing that you might notice here is that what I told you is that you just train your neural network, you now evaluate it by testing it, and you get 2 numbers, right? Test loss, or average test loss, and average test accuracy, right? This is what you get. But typically when you look at papers, books, anything, you're going to see curves, right? Now, what are those curves? What people call them learning curves. They are the same numbers tested after every epoch, or maybe every couple of epochs of training, right? So what happens in practice? Well, in practice, you can never let your stochastic gradient descent to converge in the sense that you see no change in your weights, right? So your weights are going to get always updated, right? But initially, they get updated majorly. At some point, they get updated minorly, right? But it's hard to see it. What you do usually, you're going to put one maximum number for the epochs that you're doing, right? So you would say, I'm going to go over this data set at most 40 times, right? Not more than that. But then you want to make sure, like, okay, if I have done 40 epochs, is it good, or was it like was I just too impatient, right? How you can do it, you could say, okay, let me train it for 3 epochs, right? And after the 3rd epoch, I test. I see how much it works on the test set, right? Now, probably you do not get the best accuracy and loss, but it's definitely better than what you would have started with, just a random guess, right? So it gets a bit better. You would say, okay, it's not enough. I need better, right? So you can do another 3 epochs. Again, you test it, right? You do another 3 epochs. Again, you test it. And you keep on doing towards the very end, right? After every couple of epochs, you test it once. And then you plot these values, right? Your test accuracy should obviously go up, right? Your test loss should obviously go down, right? But these are very indicating metrics, because if you don't see that, or if you see it, for instance, we're going to talk about it in chapter 3, coming down and again going up for your loss, or the accuracy going up and then getting down, then you know there is a problem with your training. This is, for instance, what we call it overfitting, right? So these are indicating metrics. This is what we call it the learning curve, and you can simply compute it by testing your model after every epoch, or after every couple of epochs, depending on the computation power and the problem that you are dealing with, right? So now I have given you, this is basically what I said. So once you're doing the training, after every fixed number of epochs, you just test, and then you just record those values, right? So I have given this for the particular example that we had here. I mean, there is nothing specific. I just explain what you do. So you train this guy for 3 epochs. Then you put your MNIST here. You look at the classification, right? You just compute the loss. You compute the accuracy over the test set. Again, you do more epochs, right? Again, you compute that, right? And you keep on going like this. So say, for example, you're doing 100 epochs, right? So 100 times you want to go over your data set. What you are going to do in this particular one, if you are considering a batch size of size 100, this means that you're going to do 600 iterations within every single epoch, right? Because, yeah, you have 60,000 divided by 100 is 600. So you're going to do 600 iterations in one epoch. Once you are over with that epoch, you already have updated your model for 600 times, right? Maybe this is enough. I mean, as a matter of fact, if your neural network is good enough, for MNIST, this is enough. You're going to see that the accuracy jumps from, I don't know, 20% right up to 80%, right? Like huge, very sharp curve, because MNIST is very simple. But yeah, I mean, say that it's not, right? We have a very basic neural network. So what you're going to do, you're going to say that, okay, at the end of the iteration 600, I had a bunch of weights, right? I'm going to fix that. Now I test. I'm going to see up to this point what I've done. So you're going over this data that you have. So you have, for example, 10,000 samples. For each of them, you see what is the output. You compute the loss, right? For each of them, you check whether they are doing right classification, the neural network is doing right classification right now or not. And then you average it. As I said, for not very deep neural network, with MNIST, you're going to see that after the first epoch, this value is going to be around 80%. Okay? But you might say, I'm not happy with 80%. I want more. I want 99% accuracy, right? What you're going to do, you're going to go over the next epoch, right? So you would say, okay, the first epoch is not enough. I'm going to go for epoch 2. And in epoch 2, again, you do 600 new updates, right? So your weights are getting, again, changed, improved. You, again, test it. You take the value, right? Now, if I do 100 epochs, how many test results do I have? 100 test results, right? The test result after epoch 1, epoch 2, epoch 3, till epoch 100, I'm going to plot it in a curve, right? So I'm going to say after the first epoch, the test loss was very high. The second one, it dropped, and it came down, and I see this behavior, right? So you need to see this plateau at some point, right? If you don't see the plateau, if you see your curve is still going down, this means that you have not done enough number of epochs. Maybe your learning rate was too small, right? Maybe there are some other problems. You need to figure it out. But if it's still going down, like it's very steep at the end, So if you do more epochs, it's going to get better, right? At some point, it should get plateau, right? This is where your model is actually generalizing. Just a second. And then for accuracy, you should also see the same thing, right? So you need to see, like, this is the first epoch, second one, and it's going to go up, right? And the more epochs you do, the better the accuracy get. Optimally, you want to get to 1. I mean, of course, you would never get to 1. 1 means like 100% accuracy, right? But you are always getting close to that, right? Again, if you see your curve is going up still, it's steep at the end, this means that your learning was not, your training was not fine, right? You need to still keep on doing. You need to see the plateau, right? When you see the plateau, you would say, okay, the number of epochs I have done is fine. At least with this setting, if I do more epochs, I'm not going to see much more improvement, right? This is the thing that you're going to see in your test result. Yeah, that was it. So you have a question, right? Yes, definitely. I mean, this is idealized curve I'm showing you. So in practice, this is not going that smooth, only if you have like a huge number of samples for testing, right? So typically, you start with 1 seed, and this is going to just jump up and down. But the envelope should be going up, right? So very good point. So what I am showing you here is just an idealized dummy example, right? So in practice, those curves you see it in your assignments is that it's going up and down, right? And it makes sense because you're just updating with random gradient samples, right? And this, not all the time you're doing the right direction, right? Okay, so that was it for this chapter. So sorry I took like extra more time before the break, but I really wanted to finish this. So 3 major points that we discussed here. One of them was the whole story about the gradient. We did backpropagation. This is the only way you can get gradient. Gradient is the only thing you can use for training, right? Now, if you we did the classification in the particular for the particular MNIST case. We have seen that we cannot always use any loss that we want. I mean, we need to have it smooth, and we figured out how we can do it. The final thing was the story about the stochastic gradient descent. In practice, we are working with randomized gradients. The reason is because we cannot go over the whole batch of data for every single iteration. That is impossible. We are going to always use SGD. From now on, whenever I say SGD, you just think about the mini batch SGD, okay? This is the classic way of doing it, okay?